Okay, good evening everyone. Let us begin today's session. So today's this is the week 4 session on the course on aircraft design. So first I will summarize what sir has taught in this week, and we'll go over the concepts briefly. Then I'll discuss some exercises. So in this week sir has discussed critical Mach number, drag divergence Mach number, supercritical aerofoil, effect of thickness ratio on the like this week was mainly about aerofoil and wing selection, aerofoil and wing selection. So when we are designing an aircraft, we have to choose what kind of a aerofoil and what kind of a wing we want to have in the aircraft. Okay, and so this is I think the first part of this section, like aerofoil and wing selection. Like I think there are some other concepts that will be covered in week 5. So in this week sir has discussed critical Mach number, drag divergence Mach number, supercritical aerofoil, effect of thickness ratio, effect of aspect ratio, in wing sweep, wing twist, and wing taper ratio. Okay, so these are important things when selecting an aerofoil and wing. So, I'll revise some topics. So, aerofoil terminology. So, we draw. So, aerofoil is a curved type of surface. Okay, from where if oncoming air is passed, the surface generates lift. Okay, so usually the aerofoils they are a bit like they are curved. Okay, above the mean line. So this line, okay, this straight horizontal line, this is the mean chord. Okay, mean chord of the aerofoil. No, not the mean chord, the chord of the aerofoil. Okay, and the distance from the leading edge to the trailing edge is defined as the chord length C. Chord length C. You also have a curved line, okay, around which the aerofoil is like created. Okay, there is a upper curved surface and a lower curved surface, and when you take the midpoint of these two curved surfaces, you get the mean camber line. And for most practical aerofoils, this mean camber line is above the chord line, and the leading edge. Okay, so this is known as the leading edge and this is known as the trailing edge. So the curvature at the leading edge is called the leading edge radius. Okay, and the thickness of the aerofoil is defined as like the distance between the upper surface and the lower surface. So you can see, like, if you see this diagram, so this distance is the thickness. This distance will be the thickness. Okay, so the thickness is obviously, like, the thickness is variable with the um, distance along the aerofoil. So you can see over here that the thickness is a function of the distance along the aerofoil. And if the air is coming like this, then the angle between the chord and the oncoming air is the angle of attack, alpha. Okay, so this is like a basic airfoil terminology. So when selecting an airfoil, what are the things that we consider? So we want CL alpha to be as high as possible. So you know that we can write CL as CL naught plus CL alpha into alpha. Okay, so if alpha is higher, then with a small change in angle of attack, I can generate a lot of lift. So, like, one thing is that I can generate a lot of lift, and I can do so with a small angle of attack. Okay, then we want alpha stall to be as high as possible. So if alpha stall is higher, we can pitch the aircraft up more. Okay, we can fly at higher alphas, and it increases safety also. Like if your alpha is like 4 5 degrees, then it is very easy to stall the plane. But if your alpha is 15 20 degrees, then there is more margin of safety. Okay, so this is the CL versus alpha curve, as you know. So this angle is alpha stall, and this is CL max. So if your alpha stall is on the lower side, then it is very easy to stall the plane. Okay, and there is not much margin of safety. But if your alpha stall is greater, okay, it is towards it is on the higher side, then it is there is more margin of safety. Okay, and it is uh, better. Okay, then we want CL max to be higher. So CL max is this one. Okay, so why do we want CL max to be higher? Because uh, V stall is proportional to 1 by root over CL max. So if CL max is higher, then the stall speed is lower. Okay, and we can fly the plane at lower speeds. Okay, so if CL max is higher, V stall is lower, and so we can fly the airplane at low speeds. Okay, and it again increases the safety. It can also increase the altitudes where it can take from where it can take off and land. Like you know that when we take off or land from a higher altitude, we require more velocity. Okay, so but like instead of increasing the velocity, we can also increase the CL max, and that will keep the velocity constant. Then we want CD to be as low as possible. So CD is the CD indicates the drag produced by the aerofoil. So remember that this is not the induced drag. So this is different from induced drag. Okay, uh, this is like we can write the CD as CD naught plus KCL square. So this CD, like for aerofoil, this CD will be this one. Okay, this is the induced drag. So this comes into picture when we have created a wing out of the aerofoil. So as long as we are only talking about aerofoils, this is the term that we are talking about. Then we want the Cmac to be as low as possible. So the Cmac indicates the pitching moment of the aerofoil. So when you have a cambered aerofoil, okay, which is usually the case, this produces a pitch down moment, okay, about the aerodynamic center. So we want this pitching moment to not be very high. Okay, ideally it should be zero, but since zero pitching moment is not possible, we want this to be not very high, because if there is a bigger pitching moment, then we'll have to cancel it out somehow, right? Like if we don't cancel it out, then the aircraft will pitch down, right? So we need some other kind of mechanism such as a tail or a control surface to cancel out this moment. So we want Cmac to be as low as possible. Then we want critical Mach number to be higher. So critical Mach number indicates the Mach number where the flow above the wing becomes supersonic. Okay, so if if the Mach number is less than MCR, then the whole flow along the aerofoil is subsonic. But if M is equal to MCR, then at some point along the aerofoil, the flow is supersonic. Okay, I will explain this in detail. And if M is greater than MCR, then there can be many points, or there can be a region where the flow is supersonic. So in essence, the MCR, the critical Mach number, is the upper limit where you can fly without encountering supersonic effects. Okay, So we want this to be higher, on the higher side, because then we can fly at higher velocities. Okay, there is nothing stopping an aircraft from flying at supersonic speeds. The only problem is that the drag and everything. Okay, there is going to be a huge penalty in terms of drag, so it is usually not efficient. Okay, unless you are specifically designing a supersonic combat aircraft or something, then it is fine. But like if you want to create a economical, or you want to create an airplane that consumes less fuel, then you should not fly at supersonic speeds. Then we want the Mach divergence number to be higher, on the higher side, okay, as high as possible. So Mach divergence number is a number beyond which the drag rises sharply. So if this number is higher, then we can fly at higher speeds without encountering this difficulty. Okay, now I am going to discuss about critical Mach number. So this is a aerofoil, and like you can see that the airflow is coming at Mach zero point 0.3, 0.5, 0.61 and all. So if I zoom into the aerofoil shape, so usually the airflow will come and it will accelerate up like this, okay, because of the curvature of this thing, okay, it will accelerate up. So this acceleration causes a drop in pressure, okay, so the pressure drops, okay, but the velocity it increases. So and as you can see, the more the flow has to accelerate, okay, so the more curvature there is, or more thickness there is to the aerofoil, the more uh, acceleration there will be. So especially like towards the front of the aerofoil, the velocity at this point is higher than the velocity at this point, okay, or the free stream velocity. So you can see that like let us say that the free stream velocity is Mach zero point 0.3, then on top of the aerofoil the flow might accelerate to 0.435. Okay, so this is m peak. M peak means the maximum velocity the flow has reached. So in this case it is 0.435. Okay, now let us say instead of zero point 0.3 it comes at 0.5. This is the free stream velocity. Then the flow might accelerate to 0.772, okay, above the aerofoil. And now like all this is fine, like till now we have not encountered any supersonic effects because the maximum velocity is 0.772. But when we are flying at 0.61, we observe that the flow accelerates to zero point 0.1. Okay, the flow accelerates to 1, Mach equal to 1. So this is the first time when sonic flow has been encountered on the aerofoil. Okay, so therefore this number is called the critical Mach number. So critical Mach number is the lowest possible Mach number where some part of the aerofoil experiences supersonic speed. Lowest Mach number where, okay, so now you can see, like you know that like when supersonic effects are encountered, it increases the drag, okay, uh, and it might also cause heating and all. So we like if we want to create a economical aircraft, we do not want to fly at supersonic, like we do not want to fly in the supersonic regime, okay. So in a sense, if we don't want that, then in a sense this MCR is the upper limit of where we can fly. So MCR in a way, like if we do not want any supersonic effects, then MCR becomes the highest possible speed the aircraft can fly, okay. Like you know that V stall is the lowest possible speed. Like if we fly below that, then the aircraft will fall. It will start falling. and MCR becomes the highest possible speed where like efficient flight is possible. But so but like people want to create faster aircraft, they want to reach their destinations faster. So if it is possible, then it is better to increase MCR so that the aircrafts can be flown at higher speeds. Okay, so this is a very important factor when we design aircrafts that fly at point 0.6, point 0.7 Mach, even point 0.8. Okay, so usually the commercial jetliners they fly at these velocities. Okay, so when we design aircrafts at these velocities, we have to keep these things in mind. Now, like I'm going to go into some theory of how we can find the critical Mach number. Okay, uh, so sir has covered this in his lecture. So first, like I will not go in detail, but what you can do is so our we might have a airfoil. Okay, so in this section, like he talks about how we can estimate this MCR, okay, from wind tunnel data. Now we might not have a wind tunnel, which how you can estimate MCR from wind tunnel data. So we might not have a supersonic air tunnel, so we can still estimate MCR from a subsonic air tunnel, a wind tunnel. Okay, and now you can see that it is difficult to estimate the velocity at the entire point of the like along all the points of the aircraft. So when we want to find MCR, we have to find the velocity, right? But it is difficult to measure that. Instead, what we can do is we can measure the pressure at each point of the airfoil. Okay, or we can take exam help from theoretical analysis or computation fluid dynamics. Okay, we can measure the pressure and we can try to relate the pressure difference to the velocity. So that is why like they have defined a coefficient called the pressure coefficient. Pressure coefficient, it is defined as pressure minus free stream pressure by free stream dynamic pressure. Okay, so uh, hmm. So then you can rearrange it to get this in this form, and you can make further rearrangements and substitutions and you can get this formula. Okay, the pressure coefficient is 2 by gamma m infinity square and all these terms are there. So here you have also have a term called gamma. It is a term from thermodynamics. So gamma is the isentropic expansion factor. Isentropic expansion factor of air. Okay, so you can put all of this and you can use this relation. So we now want to find the relation between CP and MCR. Relation between CP and MCR. So we know that MCR, from the definition we know that MCR is the free stream Mach number where the local value of CP, where the local value of M is 1. Okay, so we can substitute 1 over here. Okay, so this is the local Mach value and this is the uh, free stream Mach value. So we can substitute M over here and we'll get this equation. Okay, so you can see that it is similar to the above equation, just M has been replaced with 1. Hmm. Okay, so and then what you can see do is so here M infinity is actually MCR because your local Mach is 1. Okay, so M infinity is actually MCR. So then what you can do is you can plot this graph. So if you plot this graph, you will get something like this. Okay, this descending graph. Now I will discuss the other thing. Okay, so then what you can do is, so this is the first step. Obtain a plot of CPCR versus M infinity from equation 5.45. Okay, so this graph, it does not depend on the aerofoil. It is a property of air and property of, it is just a property of air actually. So this does not depend on the aerofoil shape. It is same for all the aerofoils. Uh, then what you can do is, for low speed essentially incompressible flow, obtain the value of minimum pressure coefficient on the surface of the aerofoil. Uh, so then what you have to do is, you have to, like, you have to at as low velocity as possible. Okay, because air is actually a compressible fluid. Okay, so at as low velocity as possible, let us say at Mach point 1. Okay, you have to find out this, you have to find out this CP naught. So you will put pressure sensors across the aerofoil, and then you will start the wind tunnel at Mach point 1. Then you will measure CP naught. Okay, so from this step you can get CP naught. Then you can use this CP naught and plot a variation of CP versus Mach number using this relation 5.28. So then this curve is this one. So wherever these two curves intersect, that is the critical Mach number. So I've redrawn the steps here. So first you will use equation 5.45 to draw this line. So this line is a kind of universal line and it does not change with the aerofoil. Then you have to use experimental or theoretical, like, analysis, experimental or simulated analysis, to find CP naught. So CP naught is the minimum pressure coefficient. It is a minimum pressure coefficient at very low speed. So then you will plot this, and then you will use this relation 5.28 to plot the variation of CP with Mach number. So this line, this is dependent on the aerofoil. Okay, and wherever these two lines intersect, that is the critical Mach number. So at this Mach number, essentially, what does this mean? So this is the procedure, but what does this mean? It means that, so see, this is the minimum pressure coefficient on the aerofoil, and this graph essentially plots the relationship between the minimum pressure coefficient and the Mach number for that aerofoil. Okay, so at this point, okay, so at point D, we see that the minimum pressure coefficient is equal to the pressure coefficient from this relationship. And from this relationship, we know that if the pressure coefficient is this, then the local Mach number will be 1. So that is how we find MCR. Okay, now proceeding further, so now I'll discuss drag divergence number. So drag divergence number, so this is the relationship between CD naught of the airfoil and the Mach number. So you can see that at low speeds, the drag is essentially independent of the Mach number. Okay, so the CD naught coefficient is independent of Mach number. Then um, there is a phase where there is a rise in the drag number. Okay, drag coefficient, but it is not a very sharp rise. Okay, and then after a point, the drag rises very sharply, and then after, like, when the flow becomes supersonic, the drag again falls a little bit. So the drag again falls a little bit. So this point is called the drag divergence Mach number. So it is the point from where the drag rises very sharply. So essentially, uh, So essentially, like if you fly below the drag divergence number, then the drag is not very dependent on the Mach number, and the drag is constant. Okay, and the drag is very low also. So this is again like we are speaking from the point of creating a efficient aircraft. Okay, like what we can theoretically fly. Okay, and there are supersonic aircrafts. Okay, that is not a problem. What you can do is you put a very powerful engine, and you can consume a lot of fuel, and you can fly at supersonic speeds, and you can fly above MCR, MDD, everything. But when you try to create an efficient aircraft, we try to reduce the drag. So if you fly below the drag divergence number, then the drag is low and it is not dependent on the Mach number. Okay. But after a point of time, the drag rises quite sharply, and this point is called the drag divergence number. So it is defined at the as the Mach number where dCd by dm is equal to 0.05. Now over here there is a diagram showing uh, what happens for different cases of free stream velocity. So if your free stream velocity is less than the critical Mach number, then the flow along the entire airfoil is subsonic. Now if your free stream velocity is more than the critical Mach number but less than the drag divergence number, then there is a local bubble of supersonic flow. Okay, but this is also nothing like major. There is no major penalty. Okay, for like there is like so this is there is supersonic flow, this will induce some drag, but there is no major penalty. Okay, because the flow again becomes subsonic, and it smoothly reattaches with the wing. But when your flow is more than the drag divergence number, then there is a shock wave formed. Okay, like a very big strong kind of shock wave is formed, and the boundary layer also separates, and there is turbulence also towards the aft section. Okay, so this is the scenario that we want to avoid. Okay, so and one thing you can see from here from this chart, that the drag divergence number is usually more than the critical Mach number. From this diagram also you can see that up to critical Mach number this is flat, and then up to drag divergence number there is a slow rise. So to counteract this phenomena and to fly at higher speeds, there was the invention of a supercritical aerofoil. Okay, so this is a invention which tries to delay the onset of wave drag. So what is wave drag? Wave drag is this kind of drag, okay, where the flow separates due to supersonic flow. So the main the method is that if we keep the leading edge very thick and very rounded, then the flow accelerates very fast, okay, over this section. If instead we can make this section flatter and this section, if we can camber more, then we can get the same kind of lift, but the flow will not accelerate so faster. So in this so one is the normal kind of aerofoil, and this is two is the supercritical aerofoil. So in the normal aerofoil, the flow accelerates very much over here, and then it decelerates, and so the maximum lift is produced from this section. Okay, but in a supercritical aerofoil, the objective is to spread the production of lift over the entire wing, okay, or as much of the entire wing as possible. So the thickness and the flow acceleration, that is made as gradual as possible. Okay, so in the normal aerofoil, there is a very strong shock over here, and it is also closer to the leading edge. So it is closer to the leading edge, so it will produce more drag. But in a supercritical aerofoil, there is a weak shock. So you can see over here that the shock is very less compared to this one, and it is also towards the trailing edge. So when the shock is towards the trailing edge, you experience less drag because the turbulent flow has less contact with the aerofoil. So the advantages of supercritical aerofoil are higher MDD, and the shock wave is much aft. So the shock wave is much aft, it is not towards the front. Then you also have reduced boundary layer separation. So when you have the shock wave towards the middle or the front, then there is more separation, but when you have this towards the end, then the separation is lesser. And then you have reduced shock interaction. Okay, this is again because the shock wave is smaller, and also it is towards the aft, so there is less scope of interaction. And this is a byproduct of supercritical aerofoil, but it has been observed that the supercritical aerofoil, they're thicker. Okay, so when they're thicker, they are more, there is more space inside for putting fuel and electronics, and the structurally also it is but easier to reinforce. Okay, now moving forward, so now I will discuss the effect of thickness ratio on like various aspects. So these are some historical kind of data which has been observed. So this is effect of T by C on maximum lift. So you can see that up till a point, okay, so the graphs are kind of like this. Okay, graphs are kind of like this. So up to a point, like you can increase the thickness ratio to get more lift, but after this point, even if you increase, there is no benefit. In fact, there is a decrease in the lift, and the sweet spot is around 12 to 14%. Then for for drag, okay, so effect of T by C on drag. Now you can obviously, like, you can guess that if the wing is thicker, then the air has to divert itself more. Okay, and if the wing is thinner, then the divergence of, like, the air has to change its direction by a large percentage. But for a thinner aerofoil, the air does not have to change its direction by very much. So therefore, there is almost a kind of linear relationship, not linear but proportional kind of relationship between uh, thickness ratio and CD. So if the thickness ratio increases, it causes more drag, and if it decreases, it causes lesser drag. So like you can also say that if the thickness ratio increases, then, like, because of the diversion of this airflow, it should also produce more lift, right? Like it will produce more drag, but it also should produce more lift. Now that is the case, that is this region, okay, this region of the plot. So if the thickness ratio is increased, then the lift increases, but after that it decreases. So I think that this is because of like boundary layer separation and stalling and all that. Now this is the effect of T by C on critical Mach number. So this is MCR, and this is T by C. Now intuitively, if the air has to divert itself more, okay, so in case of a thicker airfoil, the airflow has to divert itself by a larger amount. So when there is a larger diversion, the flow acceleration is also faster. Okay, so intuitively, the For thick airfoils, the critical Mach number should be lower. So T by C, if it is higher, then the critical Mach number should be lower. Because even at small speeds also, the thickness will cause the flow to accelerate and it will reach Mach 1. So that is the graph you can see from the data that this is T by C. So as the thickness increases, the critical Mach number it decreases. So this is NACA 00XX. So again 00XX means these are symmetric airfoils, okay, and these are supercritical airfoils. So uh, supercritical 641 series, okay, they have been designed as supercritical and laminar airfoils. So you can see that they have a higher Mach number, higher MCR compared to these NACA airfoils. So you can see like at 5% thickness the MCR is almost zero point 0.9, so you can fly at 90% the speed of sound, which is a very high speed. Moving forward, so these are some slides from last class that like broad classification of aerofoils based on the thickness ratio. So when thickness ratio is more than 14%, then the aerofoil stalls from the trailing edge, and there is a turbulent boundary layer with increase in angle of attack, and the separation it starts from the trailing edge and it moves towards the leading edge as alpha is increased. The loss of lift is gradual and the pitching moment has small changes. I will like graphically also summarize these things. Okay, so this is a fat aerofoil. So the advantage is that the loss of lift is gradual and the pitching moment has small changes. Okay, so these are the advantages. Then if your thickness ratio is between 6 to 14%, then it is classified as a thin aerofoil. So in this case the flow separates near the nose at a very small alpha, but it immediately reattaches. But the reattachment does not occur at a higher angle of attack. So at small angles of attack, the flow separates but it reattaches. So it does not have much penalty, but at high angles of attack, the reattachment does not occur. And because of this, what happens is that there is a immediate and abrupt change in the lift and moment coefficients. And this is almost the same case for very thin aerofoils. So very thin aerofoils will be the case where T by C is less than 6%. So similarly, like the flow separates from nose at very small alpha and immediately reattaches, and there is a separation bubble and it goes towards the trailing edge as alpha is increased. The loss of lift is smooth, but there is a large change in pitching moment. Now, if I have to summarize, then this is a summary diagram. So this is thick. So for the thick aerofoil, you can see that there is a separation from the trailing edge. There is a separation from the trailing edge, and it moves towards the leading edge as the angle of attack is increased. So the angle of attack has been increased gradually, and this separated flow it increases. So you can see that there is almost a linear relationship, okay, and therefore the loss of lift is gradual, and you can see that there is almost no change in the pitching moment coefficient. But when you have a thin aerofoil, this separation it starts from the front instead of the back. Okay, so there is a small separation bubble. So the flow has separated here, but it again reattaches. So there is a small separation bubble, and as you increase alpha, this separation bubble it grows. Okay, and at alpha stall, this bubble it suddenly like snaps, and the whole flow becomes turbulent. So because of this, there is a sudden loss in lift and a sudden change in the pitching coefficient. So you can see over here. And this is the same case for very thin aerofoil also. Uh, there is a small separation bubble and it starts from the leading edge and goes towards the trailing edge. But above alpha stall, this bubble like it snaps. Okay, so there is a like it suddenly releases. So till here it's like this, but then at alpha stall, this suddenly releases and the whole flow becomes turbulent. So there is a sudden loss of lift and pitching moment coefficient. Now moving forward, I will discuss the effect of aspect ratio. So up till now we are discussing about aerofoils. Okay, so the aerofoils, as you know, aerofoils are like, you can say, infinite wing, or you can say 2D wings. But now we are going to discuss about wings, so they will be 3D and finite. So one of the first wait one of the most important factors is the aspect ratio of the wing. So as aspect ratio, you know, it is defined as b square by s, where b is the wingspan and s is the wing area. So like what happens is that I essentially what happens is that if you have a finite wing, like this is an aircraft with a finite wing, then towards the tip of the wing, okay, like if you look at it from the side, so below the aerofoil we have high pressure and above the aerofoil we have low pressure. Okay, so uh, this is the scenario. Okay, like because of this reason only there is a upward force. Like we have low pressure at the top and high pressure at the bottom, and because of this there is a upward force on the wing. Now at the tip what happens is that since there is no obstruction at the side, so the air it flows from the high pressure area section to the low pressure section towards the tip. So it comes like this. Okay, from the below the wing to above the wing, and since the aircraft is moving forward, this creates a vortices kind of thing, okay, towards the tip. So these vortices are generated and this is known as induced drag, and this is proportional to the lift, okay, because when when the wing is producing more lift, okay, there will be there will be more difference of pressure between the upper and the lower surface. If the aircraft is lifting a small weight or it is flying at a lower angle of attack, then the lift produced is lower, okay, and there is a lower difference in pressure. But when the aircraft is producing more lift, it is, let us say, it is carrying a heavier load, or it is flying at a higher angle of attack, or it is climbing. In that case, the difference is pressure is higher, and so the induced drag is also higher, and the usually the induced drag is a more significant drag than the aerofoil drag. So you can see, you know that CD is equal to CD naught plus KCL square. So usually like this component is more significant than this component. Okay, so all efforts are made to reduce the induced drag. Now see, you cannot eliminate this completely because uh, you cannot have a infinite wing. Okay, you in the real world we have to make finite wings. So there will always be some kind of a vortex like this. Okay, but we can try to minimize it. And one of the best ways to minimize it is to increase the length of the wings. Okay, when you increase the length of the wings, there are ways to counteract this. One is to increase the length of the wings, other is to like taper the wings. You can also put winglets. So when you increase the length of the wing, okay, the vortices will also be there, but the vortices will affect a smaller percentage of the wing. So if you have a shorter wing like this, let us say like this is a long wing but this is a short wing, then the vortices like it is almost covering 50% of the wing surface. Okay, so the effect of the vortices is going to be 50%, like it is going to be very high. But if you have a longer wing like this, then the vortices are going to affect like 10 or 20% of the wing, and 80% will behave as the aerofoil only. So this is the graph you can see of CL versus alpha for different aspect ratios. So as the aspect ratio increases, the wing span also increases, and the wing becomes more like the infinite wings. So you can see that at a equal to 1 the CL is very poor. So a equal to 1 might correspond, AR equal to 1 might correspond to this case. Okay, it might look like this. So the CL max is very low, and as you increase the AR, the CL max it increases and it approaches the aerofoil CL max. So this is the aerofoil CL max, and you can see that above AR equal to 8, the wing performance is almost similar as the aerofoil performance. So this is a good enough aspect ratio. Your AR equal to 8 might look like this. Okay, so it might look like this. So from what we can understand is that long wings are better for reducing drag. Now see, this is CL alpha 3D from CL alpha 2D, like we can derive it using this formula. And you also know that the wingspan is proportional to square root of aspect ratio. So as aspect ratio increases, the wingspan also increases. And the CL by CD is also proportional to the aspect ratio. So as the aspect ratio increases, the CL by CD also increases. Okay, now I will discuss about wing sweep. So before wing sweep, let me discuss about wing twist. So wing twist is a method of twisting the aerofoil, like creating a wing by twisting the aerofoils. So you can have one aerofoil placed like this, the other aerofoil you can twist it and place like this, okay, and the other aerofoil you can twist it further and you can place like this. Like this is very exaggerated, okay, I'm exaggerating it for illustration purpose, but you can twist the aerofoils and create a wing like this. Okay, so you can see that there is a higher angle of incidence at root and there is a low angle of incidence at the tip. So you might ask that why is this necessary or why is this required? So this is, excuse me, excuse me for some time. Okay, so the wing twist is done mainly because of two reasons. One is to um, one is to give better performance during stall. Better performance at stall. So as you know that like if you have okay, so if you have a wing without any twist, okay, so this is the root, this is the tip, and if you have a wing without any twist and the wing is about to stall, then the entire wing will stall at first, stall together, okay, the entire wing will stall at the same time, okay. So this is the default thing. There is another thing that if you can no sorry if you instead if you twist the wing in such a way that there is a high angle of incidence at the root and a low angle of incidence at the tip, then what happens is that the root stalls first. So root stalls first and the tip stalls later. Okay, because the tip has a low angle of incidence, right? So the tip stalls later. So this configuration has an advantage. The advantage is that usually the ailerons are placed towards the tip of the wing. So because of this reason, the even if the root of the wing has stalled, okay, the tips will still be effective and the pilot will maintain roll control. The pilot will be able to actuate the ailerons and maintain roll control. But if the tip had stalled first or the root and the tip had stalled together, then the pilot may lose roll control, okay. So then the situation is worse, sir, right? Because the plane has stalled also and it has lost roll control. But in this twisted kind of scenario, the when the aircraft has stalled, it will still maintain control and it can recover from the stall. And the second reason for doing this is that it can also reduce the induced drag. It can reduce the induced drag. Now how can it do that? So as I said previously that the induced drag is proportional to the lift. If you are producing more lift, then the pressure differential will be more, okay, the pressure differential will be more, and because of that the vortices will be more and the drag will be more. But if you have twisted the wing, so this is again the root and the tip, and we have twisted the wing in a similar fashion. Okay, so there is a higher angle of incidence at the root and lower angle of incidence at the tip. So what happens is that this section it produces more lift. The root produces more lift and the tip produces lesser lift. Okay, so since the tip is producing lesser lift, it there will be lesser vortex and lesser drag, induced drag. So this was the advantage of twisting the wing. So one of the ways is to twist the wing uh, geometrically. So you can take the same aerofoil and then twist it and make the wing. Now obviously there is another thing that the this kind of surface or this kind of wing, it is not easy to manufacture, okay, because like you can see that it is not easy to manufacture this kind of wing, but it is like still necessary in a sense. And there is another way to twist it. In this kind of scenario, the wing actually like geometrically the wing remains untwisted, but we change the aerofoils, okay. So we change the aerofoil, so we put less cambered aerofoils towards the root and we put more cambered aerofoils towards the tip, okay. So because of this, Okay, sorry. So this will be opposite. Okay, so in this case, this is root and this is tip. So this will be opposite. Okay, so we put more cambered aerofoils towards the root and less cambered aerofoils towards the tip. So because of this, what happens is that the root produces more lift and the tip produces lesser lift. So, so because of this, again the induced drag is less, and again the root will stall first, because you know that like if aerofoil has more camber, then the alpha stall is lesser, so the root will stall first and then the tip will stall, so we maintain both the advantages. Again, like this is also difficult to manufacture, but like these are the two options of twisting the wing. Okay, now I will discuss about wing sweep. So so see, wing sweep is a method of like sweeping back. So like in a way, like we push the wings back. So this is a normal rectangular wing. If we can push the wings back, okay, if we can push the wings back, then this kind of design is called a swept wing. So the wing sweep is usually done to increase the critical Mach number. Okay, so sweep is usually done to increase the critical Mach number, and it is also used to uh, lessen the drag. Okay, so reduce the drag in case the plane is flying at supersonic. But there is another application, that if you are designing a supersonic aircraft, then supersonic aircrafts usually have swept back wings, and this reduces the drag, and it also like increases the lift. Like I'll show you how, but this is another application. So mainly what happens is that so this is the sweep angle. Okay, the sweep angle is denoted by like this. Like this is the sweep angle, as I'm showing by the arrow. It is denoted by this symbol. And so in an unswept wing, when the so in an unswept wing, when the flow approaches the wing, okay, the the approaching flow is equal to the v infinity. Okay, so uh, the MCR, the critical Mach number of the wing, will be equal to the critical Mach number of the aerofoil. It will be approximately same as the critical Mach number of the aerofoil. But if we can sweep the wings, then the approaching component of velocity. Okay, so this is the flow of the air which is towards the aerofoils. Okay, so this is going to be v infinity cos sweep angle. Okay, v infinity cos sweep angle. So now this quantity is lesser than v infinity, right? So the MCR of the wing is going to be more than MCR of the aerofoil. But you can obviously guess that if the approaching velocity is lesser, then the wing will produce less lift, and the wing will yes, so the wing will produce less drag, and it will also produce less lift. So there is a again there is a kind of compromise type of situation, because in this case your MCR is higher, okay, your drag is lower, but your lift is also lower. Okay, but this might not be the lower lift scenario. This might not play a huge role, because see, if you're flying at MCR or close to MCR, then it means that you're flying at very high velocity. So the velocity is very high. Okay, so like you can compensate the low lift with a higher velocity. So the low lift can be compensated. So when you are flying close to MCR or you are flying at supersonic speeds, usually this is very far above the stall speed. So the low lift, it does not matter as much. Okay, and if you are using a sweeping configuration, then the MCR of the wing is approximately equal to MCR of the aerofoil by cos of the sweep angle. So this one is more. The wing's MCR is more than the aerofoil's MCR. Another another like small application, not very important kind of application, but another small application of the sweep angle is if you have a tail heavy aircraft. If you have a tail heavy aircraft, or if you have aircraft where the propeller or engine is at the back, okay, then you might have to sweep the wings to push the aerodynamic center backer. Okay, so if you have an aircraft where the engine is towards the back and the CG is also very back, okay, CG is very back. So this is a tail heavy aircraft because the center of gravity is towards the back of the aircraft. So if you do not sweep the wings, okay, so let us say you create flat wings like this, okay, so you do not sweep the wings, then the aerodynamic center is going to be over here. But if you sweep the wings back, then your aerodynamic center might be shifted here, which will create a stable aircraft. Okay, so this is another small application, but this is, I don't think this is very important because you can only sweep the wings a little bit, right? Like you cannot sweep it very big amount back. So, but this is also possible. Another another application of sweeping the wings is for supersonic aircraft. So you know that supersonic aircrafts, they like when aircrafts fly at supersonic speed, a shock like a Mach cone is generated. This is called a Mach cone. These lines. So this is a shock wave essentially. So what we can do is we can uh, design the wings in such a way that they do not hit the Mach cone. Because when you hit the Mach cone, or when you fly on the other side of the Mach cone, then there might be a lot of drag and lift penalty. So this angle, the angle of the Mach cone mu. Okay, so this angle is given by sine inverse 1 by Mach number. So now if I draw the top view, then the Mach cone might look like this. Okay, this is the aircraft's nose. Now if I create a straight wing, it will be passing through the Mach cone. Okay, so this part of the wing and this part of the wing, it is on the other side of the Mach cone, and these sections are going to experience loss of lift and a lot of drag. So in this section your drag is higher and lift is lower. Okay, but inside the Mach cone over here, the lift and drag are normal, so the drag is lower and the lift is higher. So what we can do is we can sweep the wings. If this is the Mach cone, then we can sweep the wings back. So in this way, the whole wing it stays within the Mach cone, and we do not suffer the lift and drag penalties. So drag is lesser and lift is higher. But this cannot be done indefinitely. Okay, like this can only be done up to a point. Okay, uh, like if you keep on flying at higher speeds, essentially this Mach cone will come closer. Okay, so this might be for Mach equal to 2. This will be for Mach equal to 3. Okay, something like this. Like these are all rough numbers, but this is what might happen. So in that case, the Mach cone will hit the wings. Okay, and you might experience a loss of lift. So these are the applications of wing sweep. Now I will like quickly discuss about wing taper ratio. Wing taper ratio. Now you might have observed that in almost all aircrafts, okay, the wing is not plane like this. It is not like a plane rectangle. Okay, even if it is not a swept wing, the tip is usually smaller than the root. The tip is usually smaller than the root. So CT is usually less than CR. Now why is this done? Okay, so I'll explain it, but this ratio lambda equal to CT by CR, this is known as the wing taper ratio. Okay, so for a rectangular wing, your lambda is 1, which means that CT and CR are the same. So what are the advantages? So the so usually like the this is done to reduce the induced drag. Okay, so it has been analytically shown that elliptical wings they produce the lowest induced drag. Okay, so if your wing is elliptical like this, then this will produce the lowest amount of drag. But it is difficult to manufacture this elliptical wings. So what instead we do is we create rectangular wings or trapezoidal kind of wings where the tip is smaller than the root. This also achieves the same effect. Okay, and it has been observed that if lambda is approximately zero point 0.4 or zero point 0.5, then this configuration it achieves the same kind of drag as the elliptical wing. So another like why like intuitively why this will happen is that if your tip is smaller than the root, then the tip is producing less lift. Okay, so if you draw the lift curve, then so this is the lift curve. Okay, so the tips are producing lesser lift and the roots are producing more lift. Okay, so this section of the wing it is producing the biggest amount of lift. Okay, so the because of this, since the tips are producing lesser lift, there will be less vortices and less drag. Okay, less amount of vortices, less amount of drag. Okay, another advantage is that since the root is producing most of the lift, okay, you will have lesser bending moment. Okay, imagine like if this section of the wing it produced a lot of lift. Okay, then what would happen is that the wings would bend. So if this is your aircraft, the wings could bend like this. Okay, and this also happens. Okay, like even when you fly in commercial aircrafts, the wings do bend up a little bit. Okay, because like essentially like the wings are carrying the weight of the aircraft. Okay, the wings are carrying the weight of the aircraft. So if your tips they produce a lot of lift, then the bending will be more. On the other hand, if the root produces more lift and the tips produce lesser lift, then the bending will be lesser. Okay, so structurally it is also easier to reinforce. Okay, so that was the effect of wing taper ratio. Now I will go to the exercises. So this is the first exercise, that for an incompressible flow, if local area velocity decreases, then dynamic pressure will, like, what will happen? Okay, so in this case, the obviously the dynamic pressure will decrease, because you know that the dynamic pressure Q infinity, this is equal to half rho V square, V infinity square. So like this is also for free stream and also for the local case also. So if the local velocity decreases, then the dynamic pressure also decreases. Okay, now moving to the second question. This is the second question. So the wave drag, it is produced due to shock wave formation. So incompressible flow does not produce any wave drag. Okay. Um, so if you have a wing and if you have supersonic flow, then there is a shock wave over here. There is a m greater than 1. So this region has m greater than 1, and there is a shock wave. Because of this reason, the flow separates over the wing, and this turbulence, it causes drag. Okay, now moving to next question. Is the next question, that supercritical aerofoil is primarily used for. So supercritical aerofoil is primarily used for higher divergence Mach number. Okay, because like you know that wait. So supercritical is not used for more lift coefficient or more stall angle. Now there is a confusion between drag divergence number and the critical Mach number. So one thing you must keep in mind is that MDD is usually greater than MCR. Okay, and MCR is the lowest Mach number where supersonic flow is encountered. Okay, but when we are talking about supercritical aerofoil, we assume that there is some supersonic flow. Like I will show in the diagram. So you can see that even in this, when you're talking about supercritical aerofoil, you have a shock wave already. So this shock wave indicates that the flow in this region is supersonic. Okay, so there is a bubble of supersonic flow, which means that the aerofoil is moving above MCR. So like this is not really relevant to MCR, but it is more relevant to MDD. Like it tries to delay the onset of drag. Like even when you are flying at supersonic, it tries to delay the onset of drag. Okay, so now the next question. So here the answer is swept wing. Like see, increasing the thickness of the aerofoil, this is going to decrease the MCR. As you know that if you have a very thick kind of aerofoil, the airflow has to divert itself by a big amount, and this diversion will increase the airflow's velocity. Okay, so when your thickness ratio it increases, the MCR it goes down. So this is acting in the opposite way. So increasing the thickness won't help. Decreasing the thickness can increase the MCR. Okay. Next we have increasing camber. So camber again plays the same kind of role as T by C. If you have more camber, then the flow is going to accelerate more, and that will again like decrease MCR. Then the last one is decrease MDD. So this is a vague kind of option, but one thing you can remember is that MCR is lesser than MDD. So if you are decreasing MDD, then there is a chance that MCR might also decrease. So, but we don't want that. We want to increase MCR. So the only option remaining is the swept wing. And also, as I have discussed that when you have swept wings, then the flow which is oncoming to the aerofoils, they are V cos of the sweep angle. Okay, so an approximately MCR of a swept wing is approximately equal to MCR of the unswept wing by cos of the sweep angle. So this quantity is larger than that quantity. Moving to the next question. What is the relation between drag divergence Mach number and critical Mach number? So as you know, like up till now as I've been discussing, the divergence Mach number is usually more than the critical Mach number. Okay, M, M critical. Okay, so this is the second option is the right one. This is the next question. What is the thickness of NACA 0002 aerofoil? So for this, we have to remember the four-letter terminology of the NACA series. Okay, four-digit NACA series terminology we have to remember. Okay, so in this case, the first digit, it shows us max camber in 1 by 100th. Second digit, location of max camber in 1 by 10. And third and fourth digit, these show us the maximum thickness in percentage. So from this, what you can see is that max camber is 0. The first digit is 0, so the max camber is 0, and therefore the location of max camber also does not matter. So location of max camber, they have written it as 0, but the location is irrelevant because there is no camber. So you can also understand that this is a symmetric aerofoil, and therefore the third and fourth digit, they comprise the thickness. So the thickness is 0.2 into 1 by 100, so it is 0.02 or 2%. So therefore the answer is this 2%. So this is the next question. So here the answer is washout. So washout essentially means like twisting the wing. So as I have discussed, so usually we, like if this is the root and the tip, so in case of the root we have a higher angle of incidence, and at the tip we have low angle of incidence. So this is done like to prevent wing, like prevent tip stalling, to increase aileron effectiveness, and to reduce drag also, induced drag. So this is usually the configuration of twisting. So technically, like this configuration is also called washout, and wash in configuration is the opposite of this. So when you have low incidence at the root and high incidence at the tip, that is called wash in configuration. Another word written here is flap. So flaps are a kind of high lift devices. They also produce high drag. So if this is your aerofoil, usually there is a section which can be manipulated and moved down. Okay, so you can see that this increases the camber of the wing. Essentially, like this increases the camber, but it also increases the drag. So in this case, the lift is more, the drag is also more. Okay, uh, these are usually used only for takeoff and landing. So these high lift devices, they increase CL max by a good amount. Okay, so CL max is increased by a large amount, so the V stall reduces significantly. But since the drag is higher, you need more thrust to maintain the same, to maintain the equilibrium. So these are only used for takeoff and landing, and usually for takeoff and landing, the thrust is also, more thrust is also required. Now moving on, this is the next question.
Third option. Hello.
So
Third option.
what is a reflex cambered aerofoil? So chord line curves back up near the trailing edge. So this is the definition. So we'll go over the things. Okay, so one is that chord is stationary. So uh, I think it, like it does not make much sense because the chord line is always a straight line. So I don't know what it means by chord line is stationary. The second option is camber and chord are stationary. So the chord line is always flat line, and if your camber line is also flat like this, then it is a symmetric aerofoil. Like you know that if the camber line and the chord line, they are the same, like they're coinciding, then the aerofoil has no bending or no camber, and therefore it is a symmetric aerofoil. Uh, and the first option is chord line curves is flat near the trailing edge. Again, like I don't know what it means. Uh, the third option is the correct one. So a reflex airfoil, a reflex airfoil is like a cambered aerofoil, but right at the tip, okay, there is a like it curves back up. So this feature, this is the reflex feature, and because of this, it is called a reflex cambered aerofoil. You also have a cambered aerofoil like this. This is a normal cambered aerofoil. Now you can see that cambered aerofoil and reflex cambered aerofoil, they are similar, but in case of the reflex one, there is a like it curves back up towards the tip. This is just the difference. This is the next question.
First option.
Hmm. So, yes, most of the wings are using cambered aerofoils. So this is true. Most of the wings do use cambered aerofoils. Why? Because cambered aerofoils they produce more lift. Like compared to symmetric ones, cambered ones they produce more lift. So we use cambered aerofoils. And this is also true that cambered aerofoils can produce lift at zero angle of attack. So like their CL naught is greater than zero. So if you draw the CL versus alpha curve, then they're like this. So CL naught is greater than zero. And this is again done so that the aircrafts they can fly at a lower angle of attack. So if the airfoil produces lift at zero AOA, then it will not have to pitch up very much to take off or to cruise. Okay. So like this is another reason for using cambered airfoil. So the first option is the correct one. This is the next question. Now you know that here the answer is always negative. Now uh, you know that for a cambered aerofoil, the airflow is directed downwards, okay, towards the tip, and because of this, there is a pitch down moment. Okay, so the lift is higher, so the CL is the CL cambered, CL symmetric, but there is a negative CMAC. In case of symmetric, you have a zero CMAC. Okay, so that is it. So thank you for coming to this discussion session.